And I would like to thank you first. It was my great honor to present my recent work here. My name is Fanjin. I'm a doctoral researcher at UCL, in mechanical engineering and school pharmacy. My main research interest is in the optimization and active learning for nanomanufacturing for materials and pharmaceutical processes. So let me first start with the motivation why I'm doing this. So I'm working on a specific field called nanomaterials. So if you're not familiar with material science, let me introduce you these first. So there are specific categories under these called nanoparticles, microbubbles, or fibers. They're all very useful for healthcare applications like drug delivery. Maybe you have heard of it. The COVID vaccine is actually one type of application in nanoparticles. But if you really go to the lab and do some experiment with it, it's really, really a headache. Why is it? Because there are so many parameters that can change, and most of the time, those parameters are intertwined. That means if you change one parameter, another parameter goes suboptimal. And also, an innate problem with nanomaterials is that they're so small. They're much, much smaller than the strand of your hair. So it relies on very expensive characterization techniques, although it's not that small to the molecular level that you can characterize it with a plate reader. So you can't see with your naked eye, nor optimal microscope, so you have to find some million pounds SEM scanning electron microscopy and rely on them to do the characterization. I really like the example given by Brownie B that you basically change the ratio of the egg and milk and flour. You can bake your best cake at home. So you open the oven, you can see it right now. But the problem with nanomaterials is that after making them, you need to wait for a very prolonged feedback loop for it to see the result and then get it optimized. So that's basically what we have entered in the lab. We start with lab experiment, we go to do some characterization, and we see if it fits our target or not. If it's lucky, you get it right, then you're done. But if you're not, you have to go back to the lab and do another round of experiment. Because we have an audience of active learners, it's very natural to think, oh yeah, let's just use Bayesian optimization for it. And I'm putting a very classical implementation of Bayesian optimization with expected improvement. Um, I'll go back to this equation later when we go into more detail of how we actually implemented our algorithm. But let's look at the problem we're focusing on. The specific nanomanufacturing technique, which is a fancier name that describes the process that you use to make these nanoparticles, is called electrospray. If you're in the pharma field, you might be familiar with the name spray drying, but essentially it's very much like the perfume that you use every day. You have a bottom, you have a bottle of liquid, and then it has an atomizer on the top. When you press it, then the liquid will be drawn out and will be form very, very tiny little droplets. And fortunately, here we're using some volatile solvents so that the solvent will evaporate and leave all the residues, which turn out to be tiny, tiny particles. And electrospray is just an advanced version of the spray drying and makes much, much finer particles and gives us a broad range of particles we can make by changing its processing parameters, as you can see from here. Let me bring up my laser pointer. Yes, cute. And by changing the size of the particles, you can actually use them for a lot of different applications. For example, the one I just mentioned, the COVID vaccine, is actually nanoparticles below 200 nanometer range. And if you are to make some long-acting injectables, for example, for hormone treatment, or for example, for quantum dots or microbubbles, for medical imaging, they all have different size requirements. So that being said, we need to optimize the processing parameters in the lab. And another aspect of optimization for electrospray, it actually falls in the avoiding some invisible parameters. Here, I mean avoiding experiment failures. Because sometimes, I don't know if you have encountered this before or not, Bayesian optimization might just recommend you some set of parameters. You try to implement those parameters in the lab and it just don't work probably. And then I'm not saying most of the time, but sometimes it will happen. It's a lab, we can never predict. So if you think about this, it's actually a quite complicated optimization problem. And how do we do this actually in practice in the lab? So if I go to the lab and ask my dear colleagues in the lab, they will say, based on experience, just try and error. If you know, you know. If you know the best parameters, you will be able to make them. But that's absolutely, we as computational theorists, people who study these, will not be in favor of these statements. So formally, we will frame these as two things to address. One is target-driven optimization. Why do I call it target-driven? Because all of the previous Bayesian optimization we have heard today is about maximizing or minimizing. Let's say most of the time maximizing. Let's say maximizing the yield of something, maximizing the stuff that you make to capture CO2, or maximizing the ability to, as antibiotics, let's say. But in this case, maximizing the size of a particle doesn't make sense, or minimizing it. And that's one problem we're trying to address. And another problem is called a priori unknown constraints. That's essentially the constraints you don't know beforehand before you go into the lab until you do some experiment and see, oh, actually this set of parameters wouldn't give me anything. So what I proposed in these constrained composite Bayesian observation work is combining two pillars into one piece so that we can use it for the electrospray optimization and also many other nano manufacturing processes. So it has two important aspects. One is the constraint and the other is the composite. So for the composite Bayesian optimization, luckily we have actually both authors of this paper here in the audience. So I'm not going to the mathematical details of how this was derived, but I will give you a very intuitive explanation of how this will work. So think about if you're familiar with Bayesian optimization and you applied Bayesian optimization before, what would be a straightforward way to apply Bayesian optimization? Is converting this target matching problem into a minimization problem, which is to minimize the distance of the stuff that we just made to the target product that you want. And you can, of course, use a Gaussian process to model this distance, and this will be the posterior distribution you have and the result. But some people might capture there's something wrong here already. What is not wrong is what is not right is that the distance cannot be negative, right? Because it's a distance, it shouldn't be a negative thing. So what composite Bayesian optimization essentially does is that it leaves the Gaussian process, your surrogate, to model the stuff it should do. In this case, we're modeling the size directly, and then we leave that distance function later on. When do we apply it? At the acquisition function. So this goes how composite Bayesian optimization works. Is essentially you apply the negative square distance directly to the posterior distribution, and this is what we have called the gray box optimization. So you have something that is analytically tractable and another thing that is the black box that you're trying to model. You're separating these two parts so that it may give you better performance. I mean, spoiler alert, it does give you better performance. And another huge pillar in the CCBO algorithm is that it has that specific part that tracked the experiment feasibility. And here, essentially, we have built a classifier model and we extract the probability of experiment success of, well, the X, which is essentially the experiment parameters, and plug that into the acquisition function. And then you will be able to use Bayesian optimization to find out what would be the next recommended experiment. So going on, knowing that we have developed the theoretical framework, we're thinking, okay, let's just test it. But first, maybe in silico, because I don't want to get my supervisor frustrated of wasting a lot of materials. So what I did was that I curated this scaling law based, well, this was a study years ago on electrospray, studying the relationship between different processing parameters and the final yielding droplet size. And I have curated this simulated electrospray equation plus the feasibility zones, which essentially is a different, we have one parameter we are optimizing, which is the solvent, and we know that different solvent might not work under a specific flow rate region. And you can see that we tailored some feasibility zone, and be aware this is unknown to the GPU or Bayesian optimization process beforehand, and we only get the result of whether it's feasible or not after doing the experiment. And here are the results. So if you look at the left, you see the green line, which is the vanilla Bayesian optimization. This is the result it would look like if you just implement the vanilla Bayesian optimization, just use the Gaussian process to model the distance instead of modeling the size. So that is black box Bayesian optimization. And on top of it, you have constraint BO, which is adding the constraint part to the vanilla Bayesian optimization. You see this is a little bit improvement, but not much. But one thing that really improved is that if you look at the graph in the middle, is that it reduced a lot of failed experiments. This will make experimentalists extremely happy because they never get frustrated, go to lab, they get something at least, not something that is not working. Uh, what is really good is that after adding the composite part, to the constraint BO gives us the blue line, which is a drastic, I would say, improvement of the performance that helps us reach the target within a few iterations. And upon the request of our dear reviewers of the paper, we have added the benchmark against the different state-of-the-art methods, such as Atlas, Summit, and Dragonfly. And just to show that Atlas is the only library that explicitly allows a priori unknown constraint Bayesian optimization. And on the right, I tried really hard to visualize these, thanks to the relatively low dimensionality problem I'm dealing with. And you can see how nicely CCBO selects experiments. And after having this in silico result, I was really happy. I went into the lab and talked to my peer colleagues, and I said, "Do you want to have a challenge against AI?" And they are happy to take into this survey. And it turned out none of them beat CCBO after 3 iterations. And I'm talking about human at advanced level who have more than 3 years of optimizing electrospray in lab. And what is more exciting is that if we actually look into how human user optimize the electrospray, you see the follow pattern called one factor at a time. This actually resonates really well with what previously Morten mentioned about the quote that Douglas said, don't let a domain expert alone to design the experiment. This is what will happen. And you see CCBO offers us a quite wide range of choices in terms of experiment parameters. And knowing that everything will be helpful and my colleagues are frustrated, I myself went into the lab and did some experiments. And just to remind you, these SEM images are from real nanoparticles that can be loaded with drugs. And I wouldn't say that will be directly to the market, but yeah, it could potentially be used. And then we have set two different size targets. One is 300 nanometer, the other is 3 micrometers, so quite distinct. And you can see that within 3 to 4 runs, we will be able to actually reach the target quite nicely, plus minus 10% error range. And this work was very recently published on Digital Discovery as the front cover. And I have some take-home messages for you to consider maybe. One is that experiment will fail. It's not that it may fail, it will fail. And we do need to explicitly consider them. And next is that optimization in the context of lab experimentation is not necessarily always maximization and minimization. It could be target matching. For example, in the cases of drug release tuning, matching the material's property towards a physiological property. And then, for example, the example given previously about making a perfect glue, they might be able to use this CCPO. And finally, I would like to thank my supervisors and the sponsor funding body, EPSRC, for my PhD research. And finally, I would like to do a little advertisement for myself. I'm a final year PhD and I'm actively seeking for working opportunities in pharma and tech industries. And here are the LinkedIn and Google Scholar for myself. With that, I'm happy to take any questions.